It's odd to think of a particle being out here in a region outside of the classically allowed region for a particle. We know that it's going to be out there by some distance on the order of delta x, in the order of 1 over kappa. That's the exponential decay constant. And you might ask, can we actually capture or detect such a particle out in this forbidden region, the region which at least classically should never happen? To see it, we would need a probe which has a wavelength less than delta x. That's just because we don't want to become diffraction limited when we're looking for this thing. Which means that if I divide both sides by the other, we would need a 1 over lambda greater than 1 over delta x. Which means that we would need, it's an h. For example, a photon to probe the existence of this thing. Which is bigger than h over delta x. That means we would be adding a photon with kinetic energy k on the order of p squared over 2m. Or h squared kappa squared over 2m. And if I remember what kappa is, this is h squared over 2m u naught minus e over h bar squared. Which is going to be something like 2 pi squared u naught minus e. So, in order to see this particle out here, I'm going to have to hit it with a probe that's sufficiently energetic that I'm actually going to increase its energy by an amount bigger than the deficit by which it's lower than the classical barrier. So if this is u naught up here, and this is e down here, I'm going to end up giving it more energy. Thus, it's not going to ever really be measurable because we'll never know whether or not the particle was out there when it shouldn't have been, or we'll just think that it got out there because we actually accidentally added some energy to it and it managed to escape from being inside the box. So we still have some of the same old features from our uncertainty principle days when we started thinking about quantum mechanics. That the particle in the box solution behaves in concordance with the uncertainty principle.